So we are probably going to do some more scale diagrams in the near future because they kind of tie into this as well. So, but what we're going to look at now is we're going to look at resolution of force vectors. Okay, so it sounds more complicated than it actually is. So if you've got a force at an angle, you quite often want to split it into its horizontal component and its vertical component. This is quite useful when we're doing forces. It's also quite useful when we move on to do more projectiles. You know, at National 5, you had horizontal projectiles. At higher, you have ones at an angle. Okay, so it's important to be able to do this resolution of force vectors, and what it is it's just using trigonometry. So using your SOHCAHTOA, if you can remember how to do that. So that's why I've written in our opposite and our adjacent sides of that triangle. So if F is our force, so we'll be given, there's a force F, so it could be 10 newtons at an angle of 20 degrees, okay? And you need to work out what the horizontal component is and what the vertical component of that force is, because you'll use them in different ways. So the vertical component, obviously, is the opposite side of that triangle. So we'll call that Fy. And the horizontal component, Fx, is the adjacent side of that triangle. Okay, so if we look at SOHCAHTOA, if we look at the adjacent sides, we can do cos theta is adjacent of hypotenuse. Yeah, that's right, isn't it? Yeah. So the adjacent is Fx, and the hypotenuse is just the original force that was given to us. So if we wanted to arrange that to find out what Fx is, what the horizontal component is, it's F cos theta. Similarly, for the vertical components, we use sine, which is opposite of a hypotenuse. So Fy over F. So rearranging that, the vertical component of that force is the original force. Oh, sorry, not cos, times by sine theta. Okay, and that's only if the angle is that angle there. Obviously, if it was a bit different, you'd have to do something else. Okay, so it's important to look at horizontal and vertical components of forces when we're using things like F equals ma, because quite often the friction will be acting horizontally. So you need to look at the sort of opposite force to that, so the horizontal component of the force, because the vertical component of the force will be balanced by the weight downwards. So it's actually the horizontal component that we're looking at if we're looking at any other horizontal forces. So, example 13. A crate is pulled along the ground at a steady speed of 2 meters per second. So let's just highlight that. 2 meters per second by a force of 120 newtons acting at 30 degrees to the horizontal as shown. So we've got 120 newtons at 30 degrees. Calculate the force of friction on the crate. So we've also got, I'm going to label that FR for frictional force, so F little r. So it's a steady speed, so what do we know about the forces? Balanced, yes. The horizontal forces are balanced. Okay, so we need to find out the horizontal components of that force, and then we can say that it's balanced with the friction. Okay, so Fx, if you can't remember that, if you want to, you can draw yourself a little triangle where that's 120, that's Fx, that's 30 degrees, and do SOHCAHTOA from there on. Or you might just remember that it's F cos theta. So 120 cos 30. And I'll just leave it at that until we put it into any equation, just because it's a bit easier that way, rather than going point something or other if there's any points. So steady speed balanced forces. So the force of friction is equal to the x, the horizontal component of the force. So the force of friction is going to be 120 cos 30, and then you put that into your calculator. I think it comes out to be 104 newtons. So it's important to remember, if the force is given to you at an angle, you have to split it into its components to be able to answer the question. Okay, if you've got that, have a read through the next one. It's not a steady speed anymore, it's acceleration. Okay, am I okay to move on? Is anyone still writing up? So, example 14, a man pulls a garden roller with a mass of 100 kilograms with a force of 200 newtons acting at 30 degrees to the horizontal. So we've got a diagram there already, which is quite nice. If there's a force of friction of 100 newtons between the roller and the ground, what is the acceleration of the roller? So it's not a constant speed anymore, so the forces aren't balanced. So we're going to have to use F equals ma. Okay, but again, we need to have the horizontal component because that friction is horizontal, so we need to know what the horizontal the other side is. Okay, so I'm just going to redraw, but I'm not even going to attempt to draw a man with a roller. I'm just going to put a box. So it's 100 kilograms, and we've got a frictional force of 100 newtons back the way, and our forward horizontal force is going to be 200 cos 30. Again, if you prefer to draw yourself a triangle, and work it out, you can do. So we know it's accelerating and we want to find the acceleration. So we do F, unbalanced force is mass times acceleration. So the unbalanced force is 200 cos 30, take away 100 is 100 times by the acceleration. So I believe that's 173, take away 100. So the acceleration is going to be 73 divided by 100, which is 0.73 meters per second squared. Okay, that's all I want to, the theory that I want to do. I'm not going to do the next example because it takes a little bit of time to do and we've not got that much time left. So if you want to just continue with the question booklet where you got from, you can now do pages 6, 7 and 8.